Electronic billboards, data storage, even mobile phones are all pushing up demand for electricity in our cities. Now, an army of engineers is trying to wean these cities off electricity produced from fossil fuels. They are looking for new ways to generate clean power using unlimited natural resources. In parts of the world with clear skies, that means power from the sun. In the Nevada desert, technical director Brian Painter and his team face the biggest challenge of their careers.
It's technology that was, developed by, literally rocket scientists in the middle 80s, and this is the first commercial venture for this technology.
They are building a groundbreaking solar thermal power plant, and it must be finished in less than 6 months. Crescent Dune's solar thermal power plant doesn't use conventional solar panels. Here, over 10,000 mirrors called heliostats are being built around a 195-meter tower. The heliostats will focus the sun's rays onto a special receiver at the top of the tower. This concentrated solar energy will be used to create steam that will produce electricity.
When you're driving through the heliostat field, it's like driving through a big mechanical forest. It's steel, it's computer-controlled systems, and it's glass.
So far, just 1,400 of the 10,000 heliostats have been installed. Eventually, they will cover over 5 square kilometers of desert. The project requires so many that a temporary factory has been built on site. It churns out 80 heliostats per day, thanks to manufacturing processes lifted straight from an automotive plant. Every one is designed for a specific spot on the desert floor. Getting them all to work together creates a mammoth headache for Tim Connor.
We have to go through this initialization and calibration for each individual heliostat, all 10,348, before they can be operated as a collector field.
Each heliostat consists of 35 mirrors or facets, every one of which must be perfectly positioned to focus the sun's rays on the top of the tower.
Each heliostat has a focal length, and each individual facet is slightly curved based on the distance it is from the tower and the receiver. What I'm doing here is running the heliostat through the range of motion for the elevation, and we take it from the +90 to the -10 position.
Some of the heliostats are more than half a kilometer from the receiver.
What you see now is the concentrated energy from a single heliostat. You can imagine the intensity, the thermal intensity on the receiver with 10,348 heliostats focused all at one time. The amount of energy with all the heliostats pointed at the receiver would melt aluminum in a matter of seconds.
Once the sun's rays hit the target, the precise position is recorded and the calibration is complete. What happens once the sun's rays hit the top of the receiver makes this power station unique. The sun's energy is used to heat molten salt to over 530 degrees Celsius.
The salt that we're using in this system is not your regular ordinary table salt. It's only found in a couple places in the world, and its value is in its density and the ability to store energy.
Salt is heated by the focused power of the sun. It is then piped into a storage tank where it retains heat for up to 10 hours. When power is needed, the molten salt is pumped to a generator where it boils water, producing steam. This steam spins a turbine generating electricity. As the salt cools, it is pumped back to the top of the receiver to be heated again.
Right now we're standing in the middle of the hot salt tank. It's a very large tank, 140 feet diameter, 40 feet tall, and it'll hold 70 million pounds of salt that is 1,050 degrees Fahrenheit.
The tank acts like a giant battery, storing the sun's energy until needed. Crucially, for a power station fueled by the sun, this means it can produce electricity long after the sun has set. And even when the sky is cloudy, it can generate electricity reliably, day in, day out.
We can actually collect the energy during the day, and then we can operate whenever we want. So essentially, electricity collection and electricity generation are two separate processes. So the utility here in Nevada is looking for us to generate reliable electricity well into the evening hours, 12 o'clock noon to 12 o'clock midnight.
Today, a key piece of the steam generating plant is being lifted into place. The drum weighs in at 95 tons, making the lift a difficult and potentially dangerous task. To withstand high-pressure steam, the drum is made of 5-centimeter thick steel plate. If it falls, it will destroy the structure it sits on and set Brian and the team back by several months.
What's that? Right now we're rigging up a steam drum. This is pretty well the last heavy lift we have on the site. We're going to set it up on top of the steel structure on top there. We don't want anybody hurt. We don't want any equipment damaged. And so there's a lot goes into this lift, a lot of planning and preparation to make this lift happen.
Installing the drum is an important milestone.
This vessel right here, it's the last part of the process in making steam. The steam travels through the piping from here to the steam turbine.
Another piece of this complex jigsaw puzzle is lowered safely into place, bringing Crescent Dunes Solar Thermal Facility a step closer to producing the electricity Las Vegas can't live without.
When the switch finally goes on, it will be a tremendous rush for everybody. I mean, we've been building for years to have this technology really take hold, and to see the facility coming together is great. But once we turn that switch on, it'll be fabulous.
When complete, the plant will provide 110 megawatts of power, enough for 75,000 homes. It might not rival the 1.4 million homes powered by London's biomass burner, but in theory, this technology could supply all the electricity Las Vegas needs.
When you look into the future, cities like Las Vegas and Los Angeles are going to be utilizing a tremendous amount of solar energy for their power needs, and this project can help meet those future requirements.